So my name is Jonathan Lacefield. I'm a member of the product team at DataStax. For the past 2.5 years, I've been focusing on helping users solve graph problems with DataStax Enterprise and DSE Graph. Along the way, I've personally I've immersed myself in the graph world. I had some fortunate, very nice mentors in the Aurelius team, Dr. Matthias Broschler and Marco Rodriguez and all those folks, as well as Dr. Denise Gosnell along the way. So today we're going to discuss one of those implementation details that not everybody really wants to talk about, and particularly from a graph database perspective, and that is supernodes. And my original title was going to be like very boring and managery worthy. And then, I was talking to McFadden over there, and I was like, well, this is my working title, dealing with property graphs with friends in Unity towards supernodes. And he told me to run with it, so we're going to do that. And now we have this wonderful title slide. Just spoiler alert, everything goes downhill from here, so I hope you enjoy this gloriousness. All right, so really we're going to do 3 things today. We're going to ground ourselves and probably formalize some discussion around what a supernode is in the context of a property model, property graph model. We're going to talk about some common patterns that I've observed, the Aurelius team has observed, DataStax team has observed, I guess we're all DataStax, that lead to supernodes, and some mitigation strategies, particularly around the modeling of property graphs. Finally, we're going to provide some practical tips for what to do when you think you have a supernode. So just a note, I do work for DataStax. This is not a vendor talk. So I will be explicit when something is DataStax specific or when it applies to a wider breadth of vendors. To that point, we are going to focus on the property side of the graph world. This is not, I don't know if this is RDF, applies to the RDF world, right? Most of my research has been on the property side, and that's what we're going to talk about. So just some grounding to get us to the supernode problem. Let's refresh ourselves on what a property graph is. We have a very simple one here in the middle, and property graph is just a representation of a graph structure using 3 main elements, a vertex, an edge, and a relationship, or excuse me, a property, which can belong to an edge or a vertex, right? We all know that. So here we have a property model representing 2 people, John and Kelly. There's a relationship, an edge between them, nose, it's bidirectional. John and Kelly have some attributes like name and looks like maybe birth date or something. And John owns a phone, an Apple phone, while Kelly owns an Android phone, right? So what becomes interesting here is when we talk about a data structure that's optimized for traversing graphs, and that's called an adjacency list. And why this is important for our talk today is that a lot of property graph databases or property graph representations in data and persistence use this adjacency list format. And the adjacency lists optimize edge retrieval. They collect all the edges to an incident vertex. So I have one vertex and all the edges right there, and they persist data in that format. So as I walk a graph, and we'll take a look at this in just a minute, it's a very quick retrieval to understand all the connected components of that vertex. So if you see on the right, yeah, that's your right. We see the adjacency list for John, we see the edge knows, and we see the edge owns, and the same for Kelly, right? And so a lot of graph databases, whether they're in memory, project onto NoSQL stores, even taking a relational view or a document store view of a graph database, will use adjacency lists because they're efficient for graph processing in the property world. But there's a trade-off, and that trade-off happens in the context of what we're going to call a supernode. And the trade-off is if I have an outlier from an adjacency perspective, right, I can run into issues when I'm performing, when I'm walking my graph, when I'm traversing. Okay, so let's talk about what a supernode is. Denise showed this, Dr. Gosnell showed this earlier. This is a graph representing patients and doctors overlaid on a US map. Hey, Ani. And for our purposes, what we're looking for and how supernodes typically show up in your graphs, they're highly connected components. And you'll typically see large areas. So like the large dots here would represent highly connected components or potential supernodes. Okay? The trick with supernodes is there's not a hard mathematical rule of when I have too much adjacency, what would cause a supernode. Right? It's going to differ depending on your application, your graph, your usage of your graph. The main theme, though, is I have an outlier that could potentially cause trouble for my graph application. What I've come to learn is that supernodes really impact most, that's probably, I could say all, that'd be too broad brushing, but most graph applications, regardless if we're talking about analytical or transactional nature. And most people have them in their graph and they're not aware of them. But they become aware as soon as they traverse a graph and they hit a supernode. I consider these like the sleeping time bombs of the graph space. And it's just really a trade-off of adjacency list as a data structure. But the important part and why we're talking about this today is for those that run graphs today, whether analytical, transactional, both, you probably have this in your graph, right? And just a matter of when, not if, you're going to run into some of these issues. So to make this more concrete, let's kind of refine the definition of a supernode. And let's look at two star graphs, right? What we have represented is essentially a vertex, just call it whatever, with adjacency around it. And by the way, for those not familiar with some of the formal graph terminology, we call two vertices, there's Denise's one, two vertices that share an edge, we call those adjacent vertices, right? So an adjacency list is just the representation of a vertex and all of its neighbors. So here, if we're traversing a graph with a vertex that's represented on the right with a branching factor of 4, no big deal. We'll probably move on regardless of whatever your implementation is, right? But we start running into issues with computational explosion when we hit things like what's represented on the left. It could be thousands, hundreds of thousands, millions of adjacent vertices. And if you look at this in isolation, this is a linear relationship between the number of incident edges or adjacent vertices and the performance you're going to get during traversal time. Now, the true supernode problem has two impacts. One's on query traversal performance. The other is on storage retrieval. Because I'm going to take an abstract view and try to not take a vendor-specific view of this problem, we're going to focus on the computational side, right? And to drive this home a little bit, we're going to use a graphic we saw this morning during Dr. Gosnell's presentation, in which she was talking about how traversals manifest themselves or map themselves to system resources, right? So let's take a look at a gremlin traversal, g.v.out something, traversing a graph. In Gremlin, there's a concept of a traversal, which represents your, lack of a better term, your query, what you're trying to do. And at every step, every vertex along the way, every path along the way, Gremlin will create traversers. Just think of those as objects, right? And they're going to use some kind of system resource. And everything works well until you get in situations like this, where I'm about to run into a supernode. And more than likely, you won't know until you've hit it, right? And this is where the combinatorial explosion happens from a processing perspective. You've just all of a sudden created a whole bunch of traversers in the Gremlin world. I'm not familiar with the underpinnings of Cypher or, let's say, Arango's query language, but conceptually I could see the same thing happening here, right? You're going to have computation, it's just physics, right? All right. Sweet. Yeah, I'm glad you laughed. The funniest part about the slide, I was practicing this presentation, and the person I was practicing with was like, you know, if you put this slide up and it wasn't in a graph context, it still applies. Like stability problems, performance issues. All right, so how you typically will find out you have a supernode is you're going to run into these symptoms. This could be at an application perspective, like I'm a dev and all of a sudden things are going great and then they're not. Or maybe I'm an operator as well, right? We're talking about outliers here. So outlier impact is on performance. You'll see maybe your P95s, everything's low milliseconds, and then you go and do a study, right? And my P95s jump up to hundreds of milliseconds or seconds, something like that. Or maybe I have an application traversal that's timing out. Stability issues, all right? If you start consuming, stability issues is interesting. I'm from a graph database perspective, but this actually happens at both an application level and the database level, depending on how you have things set up. So from an application level, just imagine you traverse a node that has 1 million adjacent vertices, and the database cranks away and returns you all that data on the application side. Well, holy cow, that's a lot of data I've got to process on the application side. Right? Something in my stack's going to become unstable when I hit one of these things. A lot of people will put safeguards, just natural limits in. So you'll be traversing and you'll get a subset of the results back. Maybe you know that, maybe you don't. And that's the scary part, you don't. You return a result that is only, maybe it's because of paging or some kind of limit, right? The first 10,000 adjacent vertices, right? And finally, it's a little shout out to our graph visualization friends. They've been working on this problem forever. And it's very similar to that application view as well. What happens in my visualization if I have like some kind of visual way to explore my graph and all of a sudden I hit a supernode and 10 million vertices pop up? What am I really going to do, right? So if you're starting to see symptoms like this in your graph today, you may likely have this type of issue. All right, so that kind of grounds us on the supernode concept itself, right? We're looking for outliers and adjacency. And the trade-off of any adjacency list implementation, again, regardless if it's in-memory, doubly linked lists, however you persist or project your graph model, is that too much adjacency causes issues. That's at its the core of what it is. So some common patterns I've noticed, and our team at DataStax and talking with users, really, if you wanted to abstract this, there's two. There is modeling itself, which would cause a supernode condition, or there's the actual data pipeline, right? And what's happening and how I'm either moving data into my graph through batch or streaming processing itself. So let's take a little bit deeper look here. So modeling could be an explicit choice, design decision, or maybe I did something implicitly and didn't really realize the impact of my action, right? So the explicit modeling mistake we see a lot, particularly for new users to a property graph model, is to do something like this. And what this shows is a relationship between a person that resides at an address, right? And typically, folks will want to normalize, for whatever reason, city out of the address. And that works great, right? Gives you a nice hierarchical, nice graph view of that relationship. Works great. And this actually works well if I'm traversing from person to city. So if I go to from person, they reside maybe a handful of residents, addresses, no big deal. Each address has one city, no big deal. Graphs are really awesome because they provide flexibility at query time. That's the concept of traversing. I explore a graph. That's why we call it traversing. As soon as you go from city to address, for a city like New York, San Francisco, Miami, bam, there it is. You'll see it, right? Same concept applies, and we've seen applied to digital asset networks, which is another nice use case for graph databases. It makes sense. In graph applications, it's a good graph problem. But as soon as you start putting aggregation points into your graph like this, with the potential of a cardinality of hundreds of thousands to more, right, you're going to run into it. Logistics as well. Logistics is interesting. I was having a sidebar with somebody outside about this, but same concept, right? We have a physical representation of a graph. We want to physically put that. We've mapped it out. Looks good. Let's go put it into our graph database, whatever that is. But as soon as I start from distribution center and I go back to truck without any kind of concept of time, I'm probably going to run into the supernode challenge itself. So when modeling your data explicitly in graph, the number one issue are these hierarchical relationships and not paying attention to cardinality. And we'll talk about some mitigation strategies there in just a second as well. All right, My favorite is this one here, because this one represents us, right? We're all people. We know a lot of people. This is the basis of like social networking. It's also the canonical model for any supernode or celebrity node type of issue. And on the surface, it looks nice. I have one vertex type, one edge type, very elegant, very extensible. I can do a lot with that relationship, right? Well, this is why we have the beebs at the very front. And Denise talked about this a little bit earlier with her keynote. And just a fun fact, I looked up exactly how many Twitter followers both Justin Bieber had and I had. He's beaten me by a little bit. So he's got 104 million followers. I have 123. I'm old, I don't get social media, it's a thing. But yeah, so, you know, if you take that in the context of graph traversing, everything's fine if you come across me in your social graph, right? You're just gonna keep on going, cool. You hit the Bieber node because of this relationship, right? If everybody's equal, and then bam, I'm having some kind of issues because I've just hit an adjacency list with 104 million records in it. All right. So let's shift gears a little bit. You know, with data modeling, I'm either going to put explicit aggregation points in my graph, or I'm going to create typically a self type of relationship without really understanding what I'm doing there and all the nuances that could go into that. So data pipelines, even if I get the model correct, right? When we create our data pipelines in our ingest, regardless, again, if this is batch or streaming, typically it's going to be both in a graph space. The business rules that define what we've modeled can change. So this is an example of what I'm talking about, and this comes from a retailer, and this happened in the real world. So what this represents is a very simple view of what would be a product catalog. And product catalogs, again, map nicely to the graph space, very hierarchical in nature, a lot of relationships. We care about both the attributes associated with products as much as we do the products and how those things relate, but it also gives us the flexibility to overlay things like supply chain and inventory into our product catalog as well. But this simple example highlights a business rule change, a change of our data that happened in the ingest process that no one on the application team understood until it happened. So a marketer at a company, a product marketer, decided to change how they wanted to view their product catalog. They wanted to go from like a individual, I'm just calling it a hammer, individual thing with a whole bunch of flexible tags, and they changed the granularity of it. And they blew out what it meant to be a product. They changed the definition of a product from being a single hammer to now hammer blue, hammer yellow, hammer green, hammer red, right? And they never told anybody on this nice product catalog team. So what happened? Well, the impact, because of the model here, is that we just blew out the number of products we had in our product vertex type. And so that nice relationship of going from a subcategory that they spent a good amount of time making sure it would work and be performant, they measured it, they tested it, went to prod, just blew up. All the rules changed on them, right? I know this is probably the only time that's ever happened, that your data changes and no one told you about it, or maybe somebody in marketing did something without talking to the folks in IT. But data pipelines, we got to be smart with what we do with the data going into our graph, protect ourselves a little bit. And I know the second point here doesn't apply to anybody in this room, but sometimes like coding defects can also result in this type of scenario. So again, the common patterns I've seen and we've seen that cause supernodes, explicit modeling, like just not really being aware, that implicit relationships, and then setting up, I would call it naive, data pipelines going in the graph, right? Because the relationships matter so much, we need to pay attention there. All right, so let's shift gears and talk about how we can mitigate, what we can do to mitigate some of these items, to kind of mitigate the impact or the potential that a supernode will make it into our graph. Anybody like the shield? Yeah? No? Okay. Okay, so I look at this as having three main things we're going to do. And Dr. Gosnell spoke about the first one a little bit, and I'm going to tease it out some as well. Know your cardinality. Profile your data. Get a good representative sample of your data. Even though these graph applications or graph problems are showing up more in transactional, more rapid application development cycles, more transactional systems, if you will, there's a lot of techniques to be used from data science when preparing the data to be used in a graph. And we'll talk about some of those in particular here. Second one is know the tools you have. So the nice part about the graph database industry, it is maturing. And we as database vendors have come across this with our customers. And we're doing things to help prevent this. Know the tools you have to prevent this type of system. If you're going to go property graph, your potential to run into a supernode is there. Your database vendor probably provides some kind of solution for you. Use it. And third, let's be smart with our data pipelines, essentially what that says. So let's dive into each one of these. Data profiling. This is actually where I get excited about data. I know it's not that great, but this can be a whole talk or conference on its own. I'm going to provide a couple of simple techniques you can use in the graph space and apply those. The real concept around data profiling in the graph world is understand not the number of entities I have or the types of entities I have, but it's really how many relationships do I have? What do these adjacency lists, what are they going to look like? And we're going to be looking for outliers. And for folks that are new to graph or don't have analytics background, I just put a couple examples up there for no reason. But two main things we can do, simple counts or looking at histograms, right? And the point of this is to find, again, those outliers. So a very simple thing we can do when profiling data for graphs is to create a single source of data which represents your adjacency list that's representative. Try to get a good sample, and that is a hard problem itself when we're talking about very large data sets. But do your best to get a good representative sample, and then count how many edges exist or coming out of one vertex, and the same with the other side. So up here, two simple counts. Y-axis are a number of adjacent vertices. X-axis are actual vertex IDs. All right, this is a made-up example. But what we're seeing here is the relationship going from V1 to V2. We would know this first vertex, 1V19, is abnormally connected in our graph. It's an outlier that we may need to pay attention to. And the same thing on the other side is to make sure to check the other side of that edge, right? Same thing here. Now, personally, I like this view a little bit better. You say they're both bar charts, but this is a histogram. And what we're looking at here are the number of occurrences of connectivity. So not just simple counts. And what's cool about this in histograms, so on the left, we have number of occurrences. And on the bottom, our x-axis is number of connections, right? And so we can see here is most of our vertices, our adjacency lists, in fact, this little sample with 60-something, 70-something vertices in it, have 100-ish or so connections. But what's cool about histograms is whenever you see this long tail to the right, that indicates an outlier. And even if it's just a count of one, you'll see it, and it immediately pops out. And that's the thing you really want to watch in graph modeling, right? So over here, we have maybe one instance of a vertex with 900 adjacent vertices. Again, this is just a mocked-up example that shows leveraging histograms for profiling for a graph space. All right, so that's great. We have some outliers. What do we do about it? This is what it comes down to in graph modeling, right? And really, it comes down to this simple choice, and this is why graph modeling is still a bit of an art. And that is, do I create a new vertex type, new node type with an edge, or do I nest that as a property in an existing vertex type? So if you apply this to some of the explicit examples we saw earlier around people, address, city, logical choice is to take city and just make it a property of address, right? And then you can act on it and act on it safely, right? This is where, and Dr. Gosling spoke about this again this morning, but this is where you'll spend a lot of time. Do I create a new vertex type, or do I nest a property in an existing vertex type? Okay. Now, I would still say the graph database market itself is youngish compared to other worlds, but as I mentioned, we are learning, and the vendors are providing some tools and techniques to solve these. Based on my research, most of the graph databases that use adjacency lists also provide this first item, vertex-centric indexes. And we'll talk about what that is, but that is a tool that's designed to help, if you've persisted supernodes, to help mitigate the chance that during traversal time you'll have issues that normally come with supernodes. To make it real simple, the selectivity thing that Denise showed earlier, this is a tool, this is a specialized index to help with that. Partitioning strategies, right? So this is a technique that we've all in the data world known for a long time, and you can either do this manually, or your database vendors will have some kind of optimization to allow you to partition your data, to break up those long supernodes and do something about them. And finally, this is where there's differentiation between the different database vendors. Some vendors will offer like hash-based indexing to help solve this problem. Others, like DSC Graph does this as well, will have term or Lucene indexing in there. So you can do different types of modeling and take advantage of some indexing to get the results. All right, so vertex-centric indexes. The goal here is to go from that linear relationship between adjacency list size and query performance, if you will, and to get it either to constant, that's ideal, theoretical ideal, I would say, but at least to make it logarithmic. And what we're going to do is essentially be selective and create some optimized indexes so that when we are selective in our traversals, we can get some local to the vertex performance gains. And we don't have to pull in that whole adjacency list and do filtering there. It'll happen for us, and we have an index structure built for that type of instance. So the flip for VCIs is you have to be selective. You have to build them, and this is, I am like 98% sure this is for all the VCI implementations, at least the ones I've been able to research. And you have to be selective in how you use them. So here, think of that person-knows relationship, right? We saw earlier in the modeling. And, I should have changed out my graph in the middle there, my chart. Oh well. So to leverage a VCI, we would do something like, instead of just give me all of the vertices that are connected to Justin Bieber, which could represent anything, like people he's following, people following him, takes in no context of time, how long has somebody been following, we can write our traversal so that we pull out all of the followed by edges from a certain point in time. And that certain point in time is going to be very, very fast with vertex-centric indexes and going to give us that nice performance gain. Okay, partitioning. From what I've seen in the graph space, partitioning comes in, again, one of two flavors. You have this manual partitioning. I used to call it sharding in old school days. And this, I believe, is what LinkedIn does for their graph. They isolate supernodes into their own schema and their own structure on their own set of servers, so that traversing supernodes kind of has its own path, and they have the ability to not impact other users, and they have resources set up to handle this explicitly. But the idea is pretty simple. I can either isolate my supernodes when I know I have them, or maybe I want to break up that supernode and create new vertices that are obfuscated for my user by partitioning, chunking, bucketing, insert any term that talks about that there. Some of the graph databases themselves can do this for you, depending on how they're set up. So I'll just break. This is like something in DSC Graph. We'll project a graph onto Cassandra. That allows us to leverage the Cassandra partitioning schema itself to change the granularity of a vertex to mitigate this type of scenario. And finally, with data pipelines, this is where we get a little more theory. And the basic concept is don't let any supernodes into your graph. And to do that, in theory, you would track connectiveness on ingest and disallow supernodes to enter, whether you're talking through batch or some kind of stream processing. In theory, that sounds great. The practical notion, there is overhead in trying to do this. So be smart when you try to apply this technique. So to apply this technique, you can do things like in your application servers, keep like some kind of probabilistic index, probabilistic metadata, some probabilistic count of connectiveness, right, and use that. Denise mentioned how Twitter did this with counters inside of Cassandra. And when I say probabilistic, it doesn't matter if you're exact. You just need to err on the side of not creating a supernode, right? So it needs to be good enough. You can also store counts, like a caching layer in your database as well, and just use them and be selective where you use them. If you have a higher propensity to create a supernode on a certain vertex type, maybe, and it happens possibly you've seen through your batch part of your pipeline, well, maybe put a stage gate there that does a quick check for the connectedness of each individual vertex as it's flowing in. And just don't allow the vertices to flow in that will create supernodes. Okay. So, mitigation strategies. Know your cardinality, profile your data, make that hard trade-off, vertex or property, and be intelligent about the impacts of doing so. And write good data pipelines that protect yourselves from doing this. All right. So what do you do if you have a supernode? Well, first, we're going to need to identify if we truly have a supernode in our graph. Most of the time, error message won't say, hey, you hit a supernode. You'll get back a timeout. You'll get back like some kind of warning that your traversal has been limited, right? Something symptomatic is going to be displayed to you as an operator or developer. And so you have the job to figure out what's going on. And if you see any of those symptoms, it's good to go check for the existence of supernodes. And to do so, we can do things like check out our application logs and correlate high CPU or high resource utilization on our database servers with the same timestamp as our app servers. Maybe we have auditing turned on in our application, and we know what traversals timed out. Sweet. Let's use those vertex types or those edges or the filter condition, something to narrow down our search for this supernode itself. You can be smart about using either your graph level or your database file level indicators of supernode. So an example of this would be in like DSC Graph or Titan or Janus as well, anything on top of the Cassandra or projecting a graph on top of Cassandra. Look for wide partitions in Cassandra. That's pretty easy to do these days. That's going to indicate, hey, I have a supernode, and I wants to know why. We can talk afterwards about how that model is projected there. But you can use, look at your database file sizes or any kind of statistics around that as well. If you're projecting your graph on top of a relational model, look up your statistics there. You should be able to figure that out pretty quickly. Third, if you have to walk your graph to find this, do that intelligently. If you're able to, maybe depending on the size of your graph, use something like an iGraph. Take your graph, put it into a singly contained analytical structure, and then do some connectiveness, right? Or run things in the background, real low processing impact. All right, once you find it, you have essentially two choices. Throw it away, right? That is the easiest thing to do. Or we're talking about some kind of form of surgery, right? And for some people with transient graphs, just deleting is cool. And it's like awesome, because that's the easiest thing we can do. The next two choices as far as like, impact from a like surgery level, we're talking like outpatient. Maybe I just chunk up that partition. I read it out. I take that adjacency list, that vertex out. I break it up into finer grained, and I just insert back in. Don't touch my model. The third and the most invasive would be changing your actual graph model to mitigate whatever's causing your supernodes to begin with, right? So you find a supernode, identify it, or you think you have a supernode, identify it, and then act on it. Remove it, change something in your model if needed. All right. So just one more observation, then we'll wrap this whole thing up. What we've come across working with users is that there are common pitfalls where supernodes will occur in your property models. So for things, and these are very common graph use cases, by the way, that we see over and over and other database vendors speak to as well. So customer 360s, watch out for your address, that city, state, any kind of country. Again, that people, that social relationship. And the third is organizational structures. And I can tell you firsthand, organizational structures don't, you think about supernodes, you don't typically think of millions of people working at a single company. But depending on how you structure that organizational structure, maybe there are parent companies which own many different companies, you could potentially have the supernode thing happen there. Digital assets and networking, again, any aggregation point. And then the second thing is really interesting when you start talking about events and adding IoT data into your graph. If you get 1 million events from one sensor a day, right, setting yourself up for, and you model that out for a supernode. So when you're ever talking about sensor data, make sure you're chunking and using the concept of time to limit that in your property model, or you have a solution around that. Product catalog, we kind of spoke about the first two, supply chains as well. Very nice graph problem and to apply graph technology to solve for, but very easily to set up supernodes. All right. So just to wrap up today, we just went through a lot of material pretty quickly. We have a good, nice grounding and formal understanding of what a supernode is, right? It is an anomaly, an adjacency list size. We talked about common patterns, how people create these accidentally or how supernodes come into your property graph, some common techniques to mitigate the chances that they will, and then what to do once you finally have, if you get a supernode, when you get a supernode in your property graph model. And then shameless plug time, we're hiring across the company, engineers, sales, marketing, the whole bit. And if you want to know more about the product, you can come talk to me out here or go to this site here. Thank you.